before we do some integrating, I wanted to show you a couple examples where we included the c, because I said before, for the definite integral, the c does not matter. Right? We don't need to put the c in. For the indefinite integral, where we're finding the function, that's the antiderivative, you must have the c or it's wrong. But for the definite integral, where it's just a number, the c is not needed. So let me show you why. All right, so here we're going to use the property of integrating and evaluating using the antiderivatives, where little f of x is the derivative and big f of x is the antiderivative. Right? And we know that another way that we can find the definite integral is to find the antiderivative and evaluate. So here's the only three examples where I'm going to use the c, include the c, and you'll see why it doesn't matter. Right? So here we're evaluating the integral of dx from 0 to 5. If there's just a dx and no number, it's understood that that's a 1. Right? We don't often include the 1 in there. So whose derivative is 1? Why, that's x. So this time we did put the c in, so we're going to evaluate x plus c from 0 to 5. Now c is not a variable, c is some constant, so we're not going to be plugging anything into c. So we plug in the upper limit, and then we plug in the lower limit and subtract. So we have 5 plus c minus 0 plus c, so that would be 5 plus c. If we distribute the negative, we'd have minus 0 and minus c. Right? Well, 5 minus 0, of course, is 5. C minus c is just 0. So the only thing that's left is the 5. Here we have another one. We have x dx, the integral of x dx evaluated from 1 to 2. We increase the exponent by 1 and divide by the same amount. Right? So the x becomes an x squared, and we divide by 2. Right, so now we have 1/2 x squared plus c, and we're going to evaluate that from 1 to 2. So we'll plug in the 2 first. Right, so that would be, 2 squared is 4, and half of 4 is 2. And then we have 2 plus c. 1 squared, of course, is 1. Half of 1 is 1/2. So, and we'll distribute the negative, so that would be a minus 1/2 and a minus c. Right, so 2 minus 1/2 would be 3/2, and notice c minus c cancels out the c. And then the last one here, we have the integral of 4 minus 1/4 x squared, evaluated from 0 to 3. Right, so we'll integrate, so the 4 becomes a 4x. The x squared, we increase the exponent by 1, divide by the same thing, so that becomes x cubed times 1/12, right? And now we're going to evaluate, and then we had a plus a c in this one, and then we're going to evaluate from 0 to 3. So first we plug in the 3 into the x's. So 4 times 3 would be 12, minus 1/12 times 3 cubed would be 27/12. And then we have a plus c. If we distribute the negative, well, that's minus 0. And minus a negative 0 plus 0, either way it's 0, and then minus c. So the only thing that's left is the 12 and the 12 minus 27/12. Everything else is either a 0. Everything else actually is a 0, right? Because c minus c is 0. So notice how the c always disappears. We don't need the c when we do definite integrals. That's just an unnecessary extra step, and don't bother, right? But make sure you have it for the indefinite integrals where you're finding the function. All right, so now we're going to do some more integrating. We're going to do both techniques. We're going to use limit of Riemann sums as well as the antiderivatives, and you should be adept at using either one. All right, I'm going to do the limit first. Right, and I did put up the formula for the power sum for this one, just because it's probably not as easy for you to remember this one. Right? And of course I have the simplified version, the expanded version, because it will be easier to work with. So first of all, let's find change in x. Right? So change in x is going to be 8 minus 0 divided by n, or 8 over n. Right, step 2, let's find x. Oops, what happened to my eye there? All right, so our first value we start off with is 0. So we have 0 plus 8 over n times j. And now we're going to plug that into the function. So we'll substitute x into the function x cubed. Now we can all agree we don't need the 0, right? So we have 8 over 9j all cubed would be 512 n cubed j cubed. All right, so now let's find the limit of Riemann sum. So we have limit as n goes to infinity, and it's the right Riemann sum with n subintervals, is going to be our change in x, 8 over n, times sigma. We're starting after the first increase, because this is a right Riemann sum, to n. And then we're plugging in the 512 n cubed times j cubed. We can now factor out the coefficient. Right, so that would be the limit as n goes to infinity, r subscript n equals, we can factor out the 512 and the n cubed. So 8 times 512 is 4,096, I believe, over n to the 4th times sigma, j equals 1 to n, j cubed. And now we'll use the power sum rules for sigma. Right, so that would be the limit as n goes to infinity, r subscript n. We have 4,096 divided by n to the 4th, and we'll just change that j cubed to what we have above there, which is n to the 4th divided by 4 plus n cubed divided by 2 plus n squared. And so we'll distribute. So we have limit as n approaches infinity, r subscript n is equal to, right? So we've got the n to the 4th are going to cancel. 4096 divided by 4 would be 1024 plus 4096 divided by 2 would be 2048 divided by n, and then plus 4,096 divided by n squared would be left in the denominator. And of course we know that the limit, when we take the limit, trying to think if that equal should be there. We'll leave it in. If we take the limit of anything that has an n in the denominator as n goes to infinity, that would just be 0, right? So this is going to be 1024. I'm thinking that the equals shouldn't be there. They're kind of picky because we're taking the limit of that. It's not, until I get to the final answer, I don't think I should have the equals in there. It's better to leave it off than include it and not have included it. It's kind of one of those things that they decided that there shouldn't be an equals in there. It's a linkage error until we get to the end, right? All right, so now we have found the limit using the right Riemann sum, right? And after a while, you'll get really good at this, right? Because, I mean, the steps are the same each time. It's not really difficult. It's a little long, but it's not difficult. And now, so let's use antiderivatives. So you should be able to use either one, right? You should be able to use power of the limit of Riemann sums when you're asked. You should be able to use antiderivatives when you're asked, right? So here we need to integrate. So we're going to increase the exponent by 1, divide by the same amount, and then we're going to evaluate from 0 to 8. So we'll plug that in. We have 8 to the 4th divided by 4 minus 0 to the 4th divided by 4. 8 to the 4th is 4,096 96 divided by 4 minus 0, and that's going to be 1024. So it's nice when they match up because it means we didn't make any errors on either side. Right, so here's the first one, and these are all in your notes. Right, and I do want you to have them both ways. Right, let's try the next one. All right, so here's our next one. Nice, easy one there. All right, so let's first of all find change in x. That's going to be 6 minus 2 divided by n, so that's 4 over n. Let's find x. Move this down, and we'll get rid of the equals. It's better to leave the equals off and not than include them sometimes. All right, so find x. All right, so we're going to, our starting value is 2 plus the change in x, 4 over n, times j, because this is a right Riemann sum. Now we're going to plug that, we're going to substitute that, as this moves down, we're going to substitute that into the function. Now I notice we don't have any x's there. So when I don't have any x's, I like to do this so I don't mess up. Right? I like to write that in as 0x and then plus 5. Right? So that would be, so our 5 there is right, is the exact same thing. So if I had the equation y equals 5 or y equals 0x plus 5, it'd be the same. All right, so now if we plug in our x into our function, we'd have 0 times 2 plus 4 over nj plus 5. Well, that's just going to leave 5. All right, and so that's what we're going to take the limit of. All right, so it's just the 5. All right, so and when I write 0x, I don't accidentally take the 2 by mistake. I know the only thing left is the 5. All right, so our starting value doesn't matter much in this, but our change in x will matter. All right, so we have change in x, which is 4 over n, sigma j equals 1 to n of 5. Well, nothing to factor out. We can just go right to power sums. This one's a quick one. So limit Rn as n goes to infinity. All right, we have 4 over n, and then the 5 becomes times 5n. The n's cancel, and that's 20. There's our limit. All right, let's do the same thing, but now let's use antiderivatives. That was a pretty short one. I have to say that's probably the easiest one of all. So now we have, we're going to increase the exponent by 1, so we have 5x, and we're evaluating that from 2 to 6. So that would give us 5 times 6 minus 5 times 2. That would be 30 minus 10, which is 20. This one is almost the same. That's how easy that limit of Riemann sums is, especially when you wouldn't necessarily write, if you're solving a problem, you're not going to necessarily write, you'll write change in x, and you might write x, but you're not necessarily going to write power sum rules for sigma. You might just do it. Right? All right, so, but I have it in the notes just to make sure it's clear. All right, so that's this one. Let's try the next one. All right, so let's use our limit of right Riemann sums, because we can still do that for this one. Right, so change in x would be 2 minus a negative 2 divided by n, so that's 4 over n. Let's find x. Right, so that would be our starting value, so negative 2 plus 4 over a change in x, 4 over nj. And now let's substitute into f of x, and of course simplify. All Right, so that would be 2 times, so that's our x, so we'll plug that in because this time we have an x, negative 2 plus 4 over nj, and then we have a minus 1. So that would be negative 4 plus 8 over nj minus 1. We'll combine the like terms, so I'm going to put it actually over here, equals negative 5 plus 8 over nj. All right, so now let's take the limit. So we have the limit as n goes to infinity. This is a right Riemann sum with n subintervals. I'm going to leave the equals off because, whoops, there goes my to be on the, whoops, go away, be on the safe side. There we go. All right, so we have sigma, oh, don't forget 4 over n. 4 over n, sigma j equals 1 to n. And then we have negative 5 plus 8 over nj. Let's split the sigmas. So we have limit, n approaches infinity. We have 4 over n sigma j equals 1 to n of negative 5 plus 4 over n sigma j equals 1 to n 8n over j. Let's factor out coefficients. So that would be limit n goes to infinity, r subscript n, nothing to factor out for the first one, 4 over n sigma j equals 1 to n, negative 5 plus, we can factor out the 8 over n, so that would be 32 over n squared sigma j equals 1 to n, and then just the j. I need a tad more space, maybe if I wrote a little smaller. There we go. And how about, there we go. I think that's in, it's all right if we don't see the, we got the change in x. All right, so now power sum rules for sigma. Notice I'm expanding as I get to the bottom. If I expanded up at the top, I wouldn't be running out of space. All right, so power sum rules for sigma. We have the limit as n approaches infinity, r subscript n, and so now that would be negative 4 over n times, oops, why did I put a negative in there? There's a negative, but it's on the 5. 4 over n times negative 5, and that's a 5. Looks like a 6. Negative 5n plus 32n squared times n squared divided by 2 plus n divided by 2. And we'll distribute, and we'll find the limit. So limit as n approaches infinity. Oh, do I have enough space? R subscript n. We left with negative 20 plus 32 divided by 2. The n squareds cancel, so that would be 16. And then we'd have plus 16 over n. And if we take that limit, we'd have a negative 4. The area under the curve, under the x-axis, is greater than the area over the x-axis. Right? So there's our answer when there's our definite integral when we did the limit of right Riemann sums. Let's see what we get when we integrate and evaluate, and hopefully it's negative 4. All right, so we have 2x, we're going to increase it by 1, squared, divide by the same thing, minus, and then the whose derivative is 1, that would be x. And we're evaluating that from negative 2 to 2. Let's simplify. So that would be x squared minus x, evaluated from negative 2 to 2. So plug the 2 in everywhere. So we have 2 squared minus 2. Put parentheses around it, minus, and then plug in the negative 2, put parentheses around. negative 2, all of negative 2 is squared, minus negative 2. And then close your parentheses. All right? Don't make silly errors just because you leave off parentheses. All right, so this would be 4 minus 2, that's 2. I'm all right if we do that. Minus, all right, and so we'll calculate that out and then we'll simplify. And we probably can leave the parentheses off because I think we can do that as a single number, right? All right, so actually maybe I'll leave it on for now. Negative 2 squared is 4 plus 2, which is 2 minus 6, which is indeed negative 4. They match, so we must be right. If we can do it 2 ways and you get the same answer, you got to be right. All right, so there we go. We can do it 2 different ways. All right? And if you needed the other part, there it is. All right, so there maybe you can see all of it. So pause if you need to change an x, and there's the rest of it. All right, so let's do the next one.